for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So in our last class, we have seen the rules that you need to remember to write IUPAC nomenclature of organic compounds having functional groups, and there we have seen an organic compound may have multiple functional groups. In the case of multiple functional groups, we have to identify which functional group is the primary functional group or the principal functional group, and to get that idea, we have to remember this order of the preference for the functional groups. In this order, the reactivity of different functional groups is derived. So because this functional group is what we call is the carboxylic acid is most reactive, so is most preferred. So this will be preference to principal functional group, even if any other functional group is there. This sulfonic acid is preferred over all other functional groups. Similarly, the COX, acyl halides is preferred over these many functional groups, and so on. This order is given. So if suppose a compound is having two functional groups, aldehyde and ketone, and then in that compound, aldehyde is the principal functional group, and ketone will be the subsidiary functional group or the subordinate functional group. This is what we have already seen. And then what else we have seen is some of the functional groups like this, like phenyl or halogens. The halogens are functional group. NO2 nitro, alkoxy that we see in the case of ethers, they are always considered as prefix substituents. Like whatever you do for the alkyl groups, if we in writing IUPAC name, we consider them always as a prefix substituents. So whatever rules that we follow for the prefix means the substituents or the branches of a chemical compound, and the same rules we will follow for naming such compounds as well. And the examples that we have seen, and these examples I'll just uh, uh, again explain. And let's see, this compound is having two functional groups. This is what we know, the carboxylic acid, C double bond O and then OH attached to this carbonyl carbon. So this is carboxylic acid and this one is ketone because two alkyl groups are attached to this carbonyl carbon. So one, this is methyl and this is the longer chain. So this is the principal functional group and this is subordinate. This ketone group is a subordinate functional group, and in naming ketone we have seen that this group, oxo group, double bond O, will be considered as a branch, and so we'll write this 4 oxo and these 5 carbon atoms are there in the longest chain, and in that longest chain this carbon of carbonyl group is also considered. So oxopentanoic acid, this will become pentanoic acid, and this compound usually, so from where we will start the numbering, from this side we will start the numbering to give these substituents lowest possible numbers. So we will start with this bromine 1 2 3 4. So 1 3 and 4 substituents will be at these positions. If you start from this end, so 1 2 3 4 5 and 7 substituents will be at the fourth, fifth and seventh position. That will not be according to the IUPAC rules. So we will have to follow this way. And why do we follow certain rules? To give a compound a name that can uniquely represent its structure. So suppose you can have, maybe you can have many multiple ways to represent the name of a compound with which you can uniquely represent. Even if the name is given, you can uniquely write the structure of that compound, and this is what we follow basically. All the rules of IUPAC is given with that sense being in mind. So this we call the one, I think these things you know, one bromo and three chloro bromo, that we here we take for all the substituents the alphabetical order, and then will come the nitro as a 7 carbon atom septane. This is what, this is ester, and this ester is what having this ethyl group, and we know esters are written their names, IUPAC names of esters. This ester group is the principal functional group here, and this is the SH group. So this one will be considered as a substituent. And so receptor with the alkyl alkanoate. So this is what, this is a methyl. So this methyl group will write, sorry, ethyl, one or two carbon atoms ethyl, and then numbering will start from this carbon atom and will go to the last carbon atom, one, two, three, four carbon atoms are there, and at fourth position we'll see in this alkyl chain, the principal chain, there is one substituent. So this substituent we know as a prefix, it is called SS is called as mercapto. So ethyl 4 mercapto. Please remember there is a space between ethyl and mercapto. Similarly here there is a space between oic acid, this part and this part, there is a space. Otherwise, in this compound, there is no space anywhere. The name of this compound, there is no space anywhere else. So only ethyl and then space ether we, uh, the, whatever this group it comes means alkyl alkanoate that we write. So between alkyl and alkanoate, there is a space, there is a gap between these two words in IUPAC nomenclature of esters. Similarly, for the acids also we provide a space between oic and after that what acid this word. And other than anywhere we don't put any space anywhere else in IUPAC nomenclature of any organic compound. So this will become then 4 mercapto and then 4 carbon atoms of butane and O8 we add here. And this organic compounds 1, 2, 3, 4, 5. Why numbering is not started from this end? Because this is a functional group and functional group is given preference over this. And OH group you can see here in this preference order. OH group is having higher priority over the double bond, means this group is more reactive than the double bond usually in most of the chemical reactions. So this numbering will start from here. So 1, 2, 3, 4, 5. So one can, this name will be pentane, 4 in 1 all. So this is pent 4 in 1 all. Why this pent? Because we know En. This is not alkane. This is in alkene. So En is here now. Similarly, you can give the name of other compounds. I hope these things I have already explained in our last class. I will move forward and will see some more compounds. Before that, these key terms are there. You should remember. I have provided it here. So organic compounds are what we know. All the covalent compounds of carbon are organic compounds mostly. The ionic compounds based on the, even though they contain carbon atoms, they are not organic compounds. Like carbonate. Carbonate contains carbon, and but carbonate, any metal carbonate is not an organic compound. And usually even carbonic acid that we know H2CO3, even though it's a covalent compound, or because this proton is acidic in this case, this is also not a organic compound. Other than that, whatever we consider usually organic compounds are covalent compounds. Even the sodium acetate is not an organic compound. Even though acetate, if you consider only acetate, this acetate ion might be the organic compound or considered in the organic compounds group. But sodium as acetate, this is compound usually, although it is there, but this compound is an organic compound. But acetic acid is an organic compound. So usually, even in the organic compound functional grouping, we have mm, also seen the names to write ions, carboxylate ions. You see here, because these ions we form because of the sodium, but usually these compounds, although this we consider them also such compounds, we form salts usually in the drugs to make those drugs dissolve in the body in the uh, aqueous medium. When we eat any drug or any pills, we take these pills, once it goes into our stomach, it could get dissolved. So many we know drugs contain carboxylic acid or something, and we just make a salt of that carboxylic acid to make the entire thing dissolve in aqueous medium. Anyway, so this compound and saturated hydrocarbon. Hydrocarbons we know carbon and hydrogen, compounds containing carbon and hydrogen only, and the saturated means there is only single carbon bond between carbon atoms. Aromatic hydrocarbons we know aromatization or something. So there are certain rules to identify whether a compound is aromatic compound or not. So the compound should be, first criteria is it should be cyclic. The second criteria is there should be alternative double or single bond, or whatever the pi electrons are there, they should be delocalized over entire ring. Whatever this ring is there, that compound. Molecules should be planar, that is not the essential criteria, or nearly planar. Like fullerenes are also organic compounds, but they are ball shaped, they are not planar molecules. And then we also look at the Huckel's rule, 4n plus 2 pi electrons. So this total number of pi electrons should be equal to 4n plus 2. And where this n is an integer, it could be 0, 1, 2, 3, and so on. And this aromaticity results in enhanced stability. A skeletal structure we have seen the shorthand method of drawing organic molecules. Carbon atoms are represented by ends of lines or bends in between the lines, and hydrogen atoms are not shown. That we have to get idea based on the valency and how whatever the leftover valency is there for each carbon atoms. Alkanes, you know, alkyl groups I have already explained. Alkene, a molecule having at least one double bond. Alkynes, a molecule having at least one triple bond. Functional groups we have seen the part of an organic molecule that imparts a specific chemical reactivity to the molecule. Substituents, these things are defined branch of functional group that replaces hydrogen atoms in a larger hydrocarbon chain. And other examples are given here. I hope I have already explained these things in that table that we have seen previously that contains different functional groups. Now let's see ethers, the organic compounds with oxygen atom that is bonded to two carbon atoms. Then in ethers we see a specific type of ether that is cyclic ether with a three atom ring, and this cyclic atom with ether with ether with a three atom ring is called epoxide. Similarly, cyclic amines are also the amines. What are amines? The amines are organic molecules in which nitrogen atom is bonded to one or more alkyl group or groups. So a nitrogen atom is attached to at least one alkyl group or even two or three alkyl groups. They are all amines. So the aziridine is cyclic amine with a three atom ring. And so we can see it. Let's see this question. Write the IUPAC names of compounds from their given structures. And so the structures are given here, and we have to find out the IUPAC name of these compounds. So this, let's look at the first molecule, first structure. So one can do numbering from this side as well, right to left, and the numbering from left to right will follow from left to right as per the IUPAC rules, because this is a functional group and functional group should be given the priority in the numbering. And so this priority means the carbon which contains the functional group should have lowest possible number. And so the numbering will start from here 1, 2, 3. If you start numbering from this side, then this OH group will take 1, 2, 3, 4, 5, 6 position. From this end, it will get third position. So the numbering will start from this side 1, 2, 3, 4, 5, 6, 7, 8. So the principal chain contains 8 carbon atoms, and at the sixth carbon atom there is one branch, one methyl group. So we will write it for 6 methyl, and this is what octanol. So octane 3ol. So this is the name of this compound 6 methyl octane 3ol. People sometimes also write the name of this compound as, so this point is important because sometimes in questions you may see this kind of naming. So this is 3 methyl 6 methyl 3 octanol. This is also an accepted name of this compound. And so sometimes people write the name of organic of this kind of compounds even in this form. So 6 methyl 3 octanol or 6 methyl octane 3O. These are the same names, and using these two names, you will reach to only the structure of this compound only. Whether 6 methyl 3 octanol or 6 methyl octane 3ol, you will write only one compound with this structure. So both the names are permissible. And that is what the aim of giving the IUPAC nomenclature is. Means with one name, you should get one unique structure. Now let's look at the second structure. Second structure will do the numbering from this end, not from this end. So 1, 2, 3, 4, 5, 6. All are carbon atoms, and these carbonyl carbon atoms are also considered in numbering. In this case, numbering will not be done in this direction because of the this functional groups should take lowest possible number. So 1, 2, 3, 4, 5, 6. So it is hexane, and what we see at the second and fourth position, this ono groups, the ketonic groups are there, carbonyl groups are there. So it will become 2, 4 dione. So hexane 2, 4 dione. C E is hexane E of hexane is retained here. Why it is retained? Because here we have written di. It is not on. If it was only one on, then we would have removed this E because there was a vowel here. So because of D, die, the E is retained in this case. So now this structure, so again we'll give the preference to this functional groups because two different functional groups are here. These both the functional groups here are ketonic functional group. In this case, two different functional groups. One is ketone and one is carboxylic acid. The carboxylic acid will be given preference, and so numbering will start from this carbon of the carboxylic acid group. So 1, 2, 3, 4, 5, 6. Total 6 carbon atoms. So the numerical root will be hexane, and what we see at the fifth position, one oxo group is attached, means the ketonic group is at the fifth position carbonyl group. So this group will write as a substituent. So at the fifth group we write oxo, 5 oxo and 6 carbon atom hexane, oic acid, and see E of hexane is now removed in this case because O is a vowel. And so 5 oxo hexanoic acid, and there is a space after oic and between oic and acid in this case. Anywhere else we have not provided any space. Now, under similar space as I explained should be between in the naming of the esters as well. Now the alkyl alkanoids, so alkyl and alkanoids should be written separately. Now this compound, so numbering will start from this end or this end. You have to understand, you should give the number, you should start the numbering from this end because E is preferred over in, and because in E comes first in the alphabetical order, they are at the same position. Other way, 1, 2, 3, 4, 5, 6. And this way, if you start numbering 1, 2, 3, 4, 5. So this here, this group is at the alkyl ion group, or the triple bond is at the fifth carbon, and double bonds from this end are at first and third carbon atoms. If you start from here, this triple bond is at the first carbon and the double bonds are third and fifth carbon. So the double bond should be given preference because the numbering, and so we start numbering 1, 2, 3, 4, 5, 6. However, in writing names, as E comes first, so E should be written first. So by mistake there is a space. So yeah. So it is hexane, 6 carbon atoms. So hexa, and as we have seen this rule for the compounds having multiple double and triple bonds. So the any of the parent alkene has to be dropped in case of compounds having more than one double or triple bond. So this compound contains more than one double or bond. So the Ne will be removed. So only hexa we will use. So 6 carbon atoms. So hexa and 1 and third position diene, two in groups are there, so we'll write diene, and in E of in is removed because Y in is there, the same vowel. So because of Y, this E of in, the last E of in is removed. So diene 5 ion is the IUPAC name of this compound. Now let's say this, see this question. Derive the structure of 2-chlorohexane. And so 2-chlorohexane means what? You have to first write the skeleton, carbon skeleton with 6 carbon atoms, and then at the second position you will have to attach a chlorine group or add a chlorine atom, and so to the carbon atoms, and this will be the structure in that case. CH3, CH2, 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 CH. This is CH because one hydrogen is replaced with the chlorine in this compound, and that is why it is chlorohexane. And so one hydrogen because valency of carbon cannot be more than 4, and so this the structure of this compound is this. So with this name you can write only one structure, this structure. This is a condensed formula, you know. You can also write a bond line formula as I suggested, and the bond line formula will be 1, 2, 3, 4, 5, 6. So 6 carbon atoms, and at the second position, the second position could be this one if you start numbering from here, or if it will be at this position if you start numbering from the left. So any one, both of compounds will be the same. Now the structure we have to write the structure of paint 4 in 2 all. So now it is paint. Paint means 5 carbon atoms are there. So we have to again write 5 carbon atoms first, and then At what position in is there? At the fourth carbon atom, there is a double bond. So we will write double bond here at the fourth carbon atom. We will write first five carbon atoms, then we will do numbering. We will write number 1, 2, 3, 4. And suppose we have started written done the numbering from left to right. So 1, 2, 3, 4, 5. So at the fourth position, we have to write put a double bond at the fourth position. In is here and 2 and the second carbon atom we have to attach one OH group. And now we have to put the hydrogen atoms accordingly, whatever the left valence is there. The first carbon atom is having a double bond, so it will require three more hydrogen atoms to complete its valency. So we'll add CH2. The second, like the fifth carbon atom, fourth carbon atom, we have to add only one hydrogen because three of the valencies are already completed because of the carbon-carbon bonds. And then third carbon atoms will have two hydrogens. Second carbon atom will have only one hydrogen because two carbon-carbon bonds and one carbon-oxygen bond is already there. And so we will add one hydrogen, and this first carbon will have CH3 group, means three hydrogen atoms because it has only one carbon-carbon bond. So that is way on write the structure from the IUPAC name of the compound. Now this compound name 3-nitrocyclohexane. So first of all, we will have to make a structure of cyclohexane, and we know it's a hexene. So cyclohexane, this is what it is given. Under 3-nitro, nitro group is at the third position, and so it means numbering will start from the carbon which contains the double bond, and so it is cyclohexene. So we'll make cyclohexane. We'll put a double bond somewhere, as you can see here. It is being put here. And then in this case, in the cyclohexane, one can start numbering from here 1, 2, 3, 4, or one can start 1, 2, 3, 4. So if the numbering is in this way, anti-clockwise, then the nitro group will be at this position. And if you do the numbering from the in the clockwise direction 1, 2, 3, then in that case the nitro group will be at this position. So whatever the way you can follow, both the compounds will be the same. So either this structure or maybe another structure you can put nitro group not at this position. You can even put this nitro group at this position as well. So in that case numbering will be 1, 2, 3. So even that will also be 3-nitro cyclohexene. Now this fourth, let's see, cyclohex 2 in 1 all. So what we see, so again we'll have to write cyclohex. There is one, 2 in, 1 in group, one double bond is there. So cyclohexane will make first the skeletal structure, then we'll put a double bond somewhere. So we'll put a double bond at this and then it is 2 in 1 all. So 1 all group is at the first position and it's a functional group. So the numbering will start anyway from the OH group, from the carbon which is attached to the OH group, and so numbering will start from here. So 1, 2, 3. So this is 2 in and 1 all. You can see here the IUPAC name. Or if this OH group you have attached, if you have written a structure and if attached OH group here, then the double bond will be here. That will also be the same compound. Or what can you do? This double bond can even be here and not at this place. So this is also the same structure. And if the double bond was here, you can put OH group here. That will be also the same structure. If this double bond is here, then you will have to put the OH group either at this place or this place. All these compounds are the same compound. And now let's see this 6-hydroxyheptanol. So now again we have to write 7 carbon atoms. The heptane, so the numerical root is 7, and the 7 hept means 7, so we'll have to put 7 carbon atoms. And heptanol, it means the first carbon atom is what? It is part of the aldehyde group, so it will be CHO group. So the first carbon atom will write CHO, and the other carbon atoms will have to put hydrogen atoms first after putting the substituents. So what are the other substituents? Is hydroxy, and the hydroxy at the sixth carbon atom. So if this is the CHO, then 1, 2, 3, 4, 5, 6. So this carbon atom should contain OH group, and after putting OH group, you can Just put the hydrogen atoms as per the rules. So what I wanted to say is, to write this structure, we have to first write carbon, 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 carbon. So three carbon atoms are already there, and there is another carbon, but this carbon is, since it is aldehyde group and numbering starts from the functional group, so you can put this as a CHO. So now this is a part of the functional group, numbering 1, 2, 3, 4, 5, 6. Now you can attach one OH group to this carbon atom, and so what OH group is attached here. The rest of the valencies of the carbon atom should be fulfilled accordingly by the hydrogen atoms, and hydrogen atoms then you can put here as given in this compound, and so this is the way you should follow. Uh, Now let's see the nomenclature of substituted benzene. Benzene, we know benzene is accepted by the IUPAC, the name itself. We'll see what are the rules to write the IUPAC name of substituted benzenes. So for writing IUPAC name of substituted benzene compounds, the substituent's name is prefixed to the word benzene. So in that case, whatever the substituents are there over the benzene ring, we write that substituent names before the benzene word benzene, and so uh, just that is how we follow the we write the names of the substituted benzenes. Now, the common names of many substituted benzene compounds are also universally used. So, there are many substituted benzene compounds. People have given a particular name. As we know, methane. Methane was a common name initially, and now methane is accepted by accepted in IUPAC nomenclature. Similarly, ethane, propane, and butane, they are all accepted in IUPAC nomenclature, but they were initially the common name, the trivial names. People have given initially whatever name this compound IUPAC had accepted. Similarly, for the benzene, these names are there. There are many substituted benzenes for which the common names are also accepted. Now, if you see the substituted benzene, this is benzene ring, and one methyl group is at one of the carbon atoms. Substitution means the hydrogen was in the benzene. All the carbon atoms contains one hydrogen, and now in this case, one of the carbon hydrogen of the is replaced by CH3 group. So one can write is a methyl benzene, because anywhere you put methyl, the numbering is not required. So you can write methyl benzene because there is no position isomer in this case if there is only one substituent. So it is methyl benzene, and this methyl benzene is also called toluene. So toluene is a common name, and this name is also accepted by IUPAC. So even in writing IUPAC name, if you use toluene, then that is also okay. So methyl benzene will be the another name for this compound. Now this is what OMe group we have seen for the ether, name of ether. This OMe group is methoxy, and this is methox, then this will be methoxybenzene. And this methoxybenzene is called anisole. The common name is anisole. Now this is what amino benzene. This is amino. The prefix NH2 is what if it works as a prefix, the name comes amino, and if it is the suffix or the primary functional group, then we write it amine. So here, writing the names of mm, substituted benzenes, even if the functional groups are there, we consider them as just substituent as a prefix. So this prefix to the amino we will use amino prefix. I have basic prefix as amino. So this is amino benzene, and this amino benzene is also called aniline. So this is aniline, benzene group 1NH2 aniline, which is a common name. Now this is nitrobenzene. There is no common name for the nitrobenzene. This is bromobenzene. Chlorobenzene, if there is a one chlorobenzene, fluorobenzene, iodobenzene, if there is one fluoro and one iodo substituent on the benzene ring. And this is what hydroxybenzene, because this is a hydroxy group, and this hydroxybenzene, this hydroxy we know, alcohol functional group, and if it is considered as a prefix in naming, so it is hydroxy and the then benzene, and this hydroxybenzene has a common name phenol. So these names is the common names of these compounds you should know. This phenol, this is aniline, this is anisole, this is toluene. Now let's look at the another rule. If the benzene ring is disubstituted, these are all the monosubstituted benzene rings. Now if the benzene ring is disubstituted, the position of substituents is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest possible numbers. So if more than two substituents are there, we start numbering, and we do the numbering in such a way that these substituents get the lowest possible number. So suppose two bromobenzenes are there here, one at the adjacent carbon atoms. So numbering will be done in this way: one, two, the in the clockwise direction, and in the anti-clockwise direction it will not be done, because if you start numbering in the anti-clockwise direction, this carbon will get first position and the substituent will be at the first position, and then second, third, fourth, fifth, this substituent will be at the sixth position. So that numbering is not preferred. This will be the numbering as per the IUPAC rule. So this will become dibromo. This is a dibromo, and these bromine groups are at first and second position. So it will become 1,2-dibromobenzene. In this case, numbering will be done in this way, because if you do the numbering in this way, this will get fourth, fifth, and this will get sixth position. So this will get fifth. That is now the preferable position in comparison to the third position if you do the numbering in the clockwise direction. So this is what this compound is: 1,3-dibromobenzene. So 1,3-dibromobenzene. Now for this compound, you can do numbering in this way or this way. Both the way you will get the same name and the numbering will be the same. It's 1, 2, 3, 4, the clockwise direction. Even in the anti-clockwise direction, 1, 2, 3, 4. The substituents are there in the same position, so you can do it anyway. Even you can choose this carbon atom 1, 2, 3 this way, then you go. If you start numbering from this carbon atom in this compound, then the numbering will be in the anti-clockwise direction. For this compound also, if you start numbering from this carbon atom, then the numbering will be done in should be done into the in the anti-clockwise direction. Now in this case there is no such preference, so one can call it as a 1,4-dibromobenzene. So this compound, IUPAC name of this compound is what? It's 1,4-dibromobenzene. And in trivial system of nomenclature, you will see it later. The terms ortho, meta, and para also are also used for disubstituted benzenes, and these prefixes are used to indicate the relative position. So 1, 2, 1, 3, 1, 4. So ortho represents 1, 2, meta represents 1, 3 substitution, and para represents 1, 4 substitution. So this is ortho substitution. For this position, this group is at the ortho position, or for this bromine is at the ortho position. For this bromine is at the meta position, or for this bromine is at the meta position. And because this is 1, 3 position, this is 1, 2 position. So 1, 2 position, ortho position, 1, 3 position, meta position, and 1, 4 position is para position. And for this bromine group, this bromine is at the para position, and for this bromine, this is at the para position. And so these are the trivial names people have started early. So this 1,2-dibromobenzene is now, it can be renamed as ortho disubstituted. This is the ortho disubstitution. Ortho is there means the disubstitution is there. So this is ortho dibromobenzene, you can say, right? So this ortho dibromobenzene, or in place of ortho we simply write O dibromobenzene. O represents, it means ortho dibromobenzene, means these two bromo groups are at the adjacent carbon on the benzene of the benzene ring. And if it is meta dibromobenzene, means this compound, means these two bromine groups are at first and third position on the of the benzene ring, and it means there is they are at the first and third carbon, alternate carbon. Now the one, so it is, one can also write as a meta complete, meta dash dibromobenzene or M dash dibromobenzene, and this compound will become para dibromobenzene or simply P dibromobenzene. So this is also one can write sometimes in IUPAC nomenclature. This is also accepted way, but this IUPAC, this is the IUPAC names. We usually follow these rules, but sometimes people also in some books they also write these names. And if these names are written even in a question or anywhere, it means if the para dibromobenzene, it means this is 1, 4 substitution. If the meta is given, means 1, 3 substitution, and the ortho is given, it's 1, 2 substitution. And this 1, 2, the substituents could be the same or they can even be different. So this bromine can be even fluorine. So this is bromine, this is fluorine. Even this can be nitro, this can be OH, anything. And the amine and so on. For tri or higher substituted benzene derivatives, but benzene derivative, as you know, there are six carbon atoms, and each carbon atom contains one hydrogen, and all the six hydrogens can be replaced by different substituents. So for tri or higher substituted benzene derivatives, the compounds are named by identifying substituent position on the ring by following the lowest locant rule. So the lowest locant rule we follow to name the substituent, whatever the rules that we have seen for the linear hydrocarbons earlier. And so the same rule will be follow lowest locant rule for numbering. For example, if you see here in this compound, if you start numbering from this carbon atom, 1, 2, 3, 4. So the substituents will be on the first, third, and fourth position. This way, numbering the substituents will get even higher number, first, fourth, and fifth. So what we will do, and if you start numbering from this carbon atom, so 1, 2, 3, 4, 5. And in this way, 1, 2, 3, 4, 5, 6. If you start numbering from this chlorine atom, the carbon containing chlorine atom, so now you see 1, 2, 3, 4. So this is in this way, if you start numbering from here and go into the anti-clockwise direction, these substituents will get the lowest locants, and so this is the preferred way of numbering. So 1, 2, 3, 4. Now the numbering is already done. So let's try to write the name of this compound. And so the name of this compound should be now here in writing their names. We have to also see the alphabetical order of the substituents. This is a chloro C. This is nitro. This is also nitro. So N. So chloro will be written first. So it is one chloro because the chlorine is at the first carbon atom. So one chloro, 2,4 dinitro, and then benzene. In this compound, the numbering will be done similarly from this carbon atom 1, 2, 3, 4. In any other way, you can try other possibilities. You will get not get the lowest locant as you see in this case 1, 2, and fourth position. From here, first, second, first, third, and fourth position. First, second, and fourth position from here. If you start from here, first, third, and fourth position. So this is even higher number because so we'll do numbering this way. You can try even all the possibilities, all the six possibilities that is total five, six possibilities will be there. So we'll write the name of this compound as what. Then again, this chloro group, the naming we'll see the alphabetical order for the substitution. Chloro comes first, then methyl comes second, methyl then nitro, N then N. So this is 2 chloro, 1 methyl, 4 nitro, benzene. So the name of this compound. Now let's see, in some cases the common name of benzene derivative is taken as a base compound. So sometimes common names of benzene derivatives are also taken as a base compound in the polysubstituted benzene rings. And for example, as we know, these names, the toluene, anisole, aniline, phenol, these common names are also accepted by IUPAC. So in this case, if there is multiple substitution on these compounds, then one can also consider this common name phenol as a base compound, or aniline as a base compound, or anisole as a base compound, toluene as a base compound. Then the other substituents should be given the position. But in this case, if this compound is considered as a base compound, numbering will always be started from the carbon atom which contains OH group. In this case, numbering will start from the carbon atom which contains NH2 group, amine group. In this case, the numbering will start from this carbon atom which contains methoxy group in the of the anisole. In this case, the numbering will start from here in the toluene. So this, in some cases, the common name of benzene derivatives is taken as the base compound, and in such cases, the substituent of the base compound is assigned a number one. So the substituent of this base compound are assigned position one, number one in the numbering of those compounds. Then the direction of numbering is chosen such that the next substituent gets the lowest locant or lowest number, and then we'll follow the direction, the numbering, then we'll do the numbering in the direction by which the other substituents get the lowest possible positions. And so in this case, the substituent appears in the name in the alphabetical order. These things we already know. But in the tri or higher substituted benzene derivatives, also meta or para prefixes are not used. So in this case, in the writing IUPAC nomenclature, also meta para prefixes will never be used for the tri or higher substituted benzene derivatives. It is permissible only for the di-substituted benzene compounds. So up to the di-substituted benzene compounds, one can write them the ortho dibromobenzene or meta ortho dibromobenzene, meta dibromobenzene or para dibromobenzene. This is permissible only for the disubstituted. For the tri and higher substituted benzene rings, this ortho meta para prefixes are not used, they are not allowed. And so let's see this is examples. So this, if suppose we can consider the numbering from here, this group 1, 2, 3, 4, and if you consider this name 1, 2, 3, 4, then this compound will be 2-chloro 4-methyl anisole. This anisole OMe, benzene ring with OMe is if I consider as a base compound, benzene ring with OMe, then what will this compound will be 2-chloro 4-methyl anisole. So 2-chloro 4-methyl. The numbering has started from this group. Anyway, the numbering will start from this group itself, even if we don't consider this as a anisole as a base compound, because the lowest locant rule will be followed. So 1, 2, 3, 4, the lowest locant rule will be this, and then in this case we'll write the name of this compound, the 2-chloro, then this is methoxy will come before methyl, this is methoxy 1-methoxy 4-methyl, the 4-methyl benzene. This is also, one can write IUPAC name of this compound also as this. So 2-chloro 1-methoxy 4-methyl benzene. Now here the methoxy and methyl we have to up to this position there is no difference. Then we'll see it here. O comes before Y, and so this will come, methoxy will come first in naming this compound. That is a substituent. So 1-methoxy and then 4-methyl benzene. This name I have already explained. Now in this case, this compound one, if aniline, I consider aniline benzene ring with NH2 substitution as the base compound. Numbering will start from here 1, 2, 3, 4. So this is anyway aniline, and we see substitution at the fourth, ethyl substitution at the fourth carbon, and methyl substitution at the second carbon. Ethyl comes first in alphabetical order. So we'll write first 4-methyl, then 2-methyl aniline. So 4-ethyl 2-methyl aniline, or another name it could be 1-amino. A will come first, 1-amino 4-ethyl 2-methyl benzene. In this case, phenol is now considered as a base compound. When using with OH group, phenol is, if phenol is base compound, then we will start numbering from this carbon atom, the carbon containing OH group. So 1, 2, 3, 4, and then the numbering is done in such a way that the other substituents are getting lowest possible numbers. If suppose the numbering is done this direction, 1, 2, 3, 4, and then 5, the position will be fourth and fifth, not third and fourth, and third, fourth are lower numbers. So the numbering is, this is the right way of numbering. Here also in these cases you can see the same thing. Now this compound will be what? The substituents are at the third and fourth position. So these are all methyl groups. So 3,4-dimethyl phenol. So this is the IUPAC name of this compound. Or one can, what else one can do is 1-hydroxy 3,4-dimethyl benzene. But usually we more commonly use this name. So this phenol as a base compound, alanine as a base compound, and anisole as a base compound, because they are, and so this aniline has certain substituents. So in base compound means what? We will see the aniline has certain substituents at different carbon atoms. This OH phenol has substituents at different position. This anisole has substituents at different position, and so on. Now let's see some other examples. And in this example, this compound, there is a cyclic alkane, and means that's the alkene is the aliphatic compound, the cyclic aliphatic compound, and this and these compounds are called alicyclic compound. And alicyclic compound is OH group is here, and then the numbering will be done. We start numbering to name this compound. Numbering will start from this OH group, the functional group. So the this 1, 2, 3. This way the numbering will be done, not in this way. And so we'll get at the third position 2-methyl substituents are there. So 3,3-dimethyl, then cyclohexane 1-ol, or 3,3-dimethyl 1-cyclohexanol. And this compound, this is epoxy compound that you know, the cyclic ether. This is cyclic ether containing three members only in this ring. These are called epoxides, and this is epoxide, and the name of epoxides are either given in this way. This O group is from the longest chain you choose, and you see which between which carbon atom this O group is present, means from which carbon atom this two carbon atom this oxygen is attached. So you write the position of that. So this is 1,2 epoxy propane. If suppose there was one CH3 group and this is CH, then you write this will become 1, 2, 3, 4. So in that case it will be 2, 4 epoxy butane. Now another name of this compound will be what? Then this group, the entire group, this ring is called oxygen. This ring is called oxygen ring, and this oxygen ring, and by the UPSC, which is recommended. So the numbering we now will start from here, always from the oxygen atom, and then the numbering will be done in such a way that the other substituents will get the lowest possible number. So 1, 2, 3. Because if you do 1, 2, 3, the substituents will get third position from this direction. 1, 2, 3. So this will become then this is substituent 2 methyl, and this is oxygen. Oxygen will be the IUPAC name of this compound. Now this compound name, the numbering will start from what? This double bond position, and so double bond position not from here, then it will get a higher number. So we'll start numbering from this position 1, 2, 3. So this one will become 3 bromo, 1 chloro, cyclohex 1 in, or 1 cyclohexene. Cyclohex 1 in or 1 cyclohexene. Now in this compound we have to choose the longest carbon chain, and the longest carbon chain you can get if you start from 1, 2, 3, 4, 5, 6, 7. So in this way you choose this one, or you choose this one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So this can also be the same. Now let's see in which direction the numbering will be done. So if we start numbering from here, 1, 2, 3, 4, the fourth position 2 substitution, and fifth position at 1 ethyl group. And if you start numbering from this direction, 1, 2, 3, the third position ethyl group, and fourth position. So this way of numbering will be preferred. So we'll do the numbering 1, 2, 3, 4, 5, 6, 7. And so now the name will be 3 ethyl at the third position is 1 ethyl substituent, and the fourth position 2 methyl groups, 2 methyl substituents also 4, 4 dimethyl heptane will be the name of this compound. For this compound, as we know, the double bond is given preference over bromine, chlorine, or the halides in the numbering, and so we'll start numbering from this in this carbon atom. This carbon atom will be the part of the longest chain. We cannot start numbering from 1, 2, 3. This will not be the substituent because it is attached to this carbon atom directly. So this is the terminus, and so the numbering will start from this carbon atom. So 1, 2, 3, 4, 5. So the longest chain contains 5 carbon atoms. 1, 2, 3, 4. If you go here, so this is a substituent, only 4 carbon atoms will be there in the principal chain. That will be the wrong one. 1, 2, 3, 4, 5. So this is 4 bromo. 1, 2, 3, 4. So this is, there is a mistake. This is 4 bromo, 3 methyl. The methyl is at the third position. So 4 bromo, 3 3 methyl, 1, 2, 3, 3 methyl pent 2 in, or 4 bromo, 3 methyl 2 pentene. And this name will not, this is also, this can also be one name as I explained just now. 4 bromo 3 methyl 2 pentene. Another way name for this same compound. This compound now, let's consider this. You have to find out the carbon chain containing this double and triple bonds. And suppose we will start numbering from, if we start numbering from this side, 1, 2, 3, 4, 5, 6, 7. And so anywhere double bond is given preference. So the 1, 2, 3, 4, 5, 6, 7. So this longest chain contains 7 carbon atoms, and what we see the substitutions at the second and third. Here also 1, 2, 3. Substitution will be at the third position. Here also the substitution starts at the third position. This is the common position for both the directions. So the numbering will be done then in that case from this side. So because the double bond here in this from this direction, the triple bond is at the first position. From this direction, double bond is at the first position. This direction at the third position, there is one methyl substituent. In this direction at the third position, methyl substituent, and this at the fourth position, propyl substituent is there from the both direction. So we'll write the name. That we'll start the numbering from this carbon atom. 1, 2, 3, 4, 5, 6, and 7 will go this way, and now this is the methyl, this is methyl, this is propyl. So PMNOP. So the methyl comes first. So this will become 3,5-dimethyl. So 3,5-dimethyl. Then at the fourth position propyl. So 4-propyl hept. 7 carbon atoms hept. 1 in 6 ion. At the sixth position double bond we see the double bond. So 6 ion is the name of this compound. So 3,5-dimethyl 4-propyl hept 1 in 6 ion. Now this compound, so the numbering will which will be the longest chain, the principal chain, this chain 1, 2, 3, 4, 5. So this chain will be the longest chain and not this one, because this one contains only 4 carbon atoms. So we'll do the numbering. The numbering will do from this direction, because the double bond you get at the second position. To do the numbering from here, you will get double bond at the third position, and so will numbering will be done from this direction. So 1, 2, 3, 4, 3, 4, 5. So at the third position, methyl group is there. So 3 methyl pent 2 in, or 3 methyl 2 pentene. This compound, if you look at the numbering, 1, 2, 3, 4, 5, and 6, not this one. So 6 carbon atoms. If you go in this direction, there will be only 5 carbon atoms. 1, 2, 3, 4, 5. So the longest chain will be this one. So the numbering will go from here to this end. 1, 2, 3, 4, 5, 6. So 4 methyl hexane 2 all, or 4 methyl 1, 2, 3, 4, 5, 6. This one is section 2 all, or 2 hexanol. So 1, 2, 3, 4, 5, 6 carbon atoms. So 4. Mhm, this is methyl, so I made a mistake here. This is 4 methyl hexane 2 all, or 4 methyl 2 hexanol. So this is the longest chain. This is the longest chain and not this one. So that was I made a mistake. You should not do the similar mistake. Now in this compound 1, 2, 3, 4, 5, this will get the first preference, first number will this. So the second group methyl, fourth group hydroxy, hydroxy comes first into the mm, alphabetical order. So this is 4 hydroxy, 2 methyl, pentanol, 5 carbon atoms, 1, 2, 3, 4, 5, 5 carbon atoms in the principal chain, so it will become pentanol. Al we add for this CHO group, considering it as a principal functional group. This is also a functional group, but the CHO group reactivity is more than OH group, and so this is the principal functional group. This is subordinate functional group, so this will be treated as a substituent or the prefix in the name. Now these things, let's see this. As I said, this compound with the CH2 CH2O group. This the group is what we call oxygen, and so this is the epoxide. The common name is ethylene epoxide. This is ethylene group, and epoxide is for the O. This compound IUPAC name, this is the common name. IUPAC name of this compound is oxirane. As we have seen, we have followed this name. So this numbering will be the two positions, so 2-methyl oxirane. So this is also a way to write IUPAC name. So this is oxirane, and if the substituents are there, so the substituents you can write the position of the substituent prefix to this word oxirane, and so you can write the IUPAC name. This compound four members ring, three carbon atoms and one oxygen. The IUPAC name of such compounds are oxytane. This is oxytane, and thus there is no common name for this compound. This compound five corner ring, four carbon atoms. These are all saturated. These are the IUPAC name is oxolane, and this common name for this compound is tetrahydrofuran. If there was a two double bond, one double bond here, one double bond here, it is called furan, and these double bonds are hydrogenated. So hydrogenated means what? One hydrogen will be added here, one hydrogen will be added here, and double bond will be removed. One hydrogen here, one hydrogen here. So the overall four hydrogen is added here, and if added to the furan, we will get this compound. So this compound's name is tetrahydrofuran. Means four hydrogen is added to the furan to get this compound. So this common name of this compound is tetrahydrofuran, and the IUPAC name of this compound is oxolane. And the six carbon compound that we see, six corner compound or six membered ring compound containing one oxygen atom, and the saturated compound is called oxane. And this is what oxane, and the common if there is a double bond, this compound is called tetrahydro. This is a pyron, and in this pyron is there, and this the four, there is one double bond and one double bond, and then O, then it's called pyron, and both the double bonds are saturated by hydrogen atoms. So we require four hydrogen atoms. So it's called common name is tetrahydropyran. This is AN, not ON, and the IUPAC name is oxalane. So as we have seen the name of this oxirane, this is oxane, this is oxirane, OXANE, oxane, for six membered ring, three membered ring, oxirane. So as we have seen the IPC nomenclature of oxirane, the same rules will be followed for the other higher members, and that you can see that this example, let's see for this oxygen, this kind of compound. So this, the numbering will be done this 1, 2, 3, because the numbering we cannot do in this direction 1, 2, 3, because this substituent only one methyl 1, and this will be 3, 3. If you go do numbering here 1, 2, 2, 3, so this will become 2, 2, 3 trimethyl oxygen, the name of this compound. Let's see the name of this compound. This, the numbering will be done from this here. This is ethoxy, this is nitro. So this is 1 ethoxy. It comes first, so 1 ethoxy and 3 nitrobenzene. Why ethoxy first? Because ethoxy comes here first in the alphabetical order. And so the numbering will be start from here. You do start numbering from here or here. You will get the substituent as 1, 2, 3, or you do numbering 1, 2, 3. The substituents are at the 1, 3 positions. So the numbering will be preferred. Now there we will see the alphabetical order from which carbon the numbering should start. So this is ethoxy E. So the numbering will start from here 1, 2, 3, and so 1 ethoxy 3 nitrobenzene. And this compound, the naming of this compound, this is a principal functional group, this is a subordinate functional group, these are also subordinate. So 1, 2, 3, 4, 5, 6. This is the principal chain 1, 2, 3, 4, 5, 6. And so the substituents are at the second position hydroxy, third position ethyl, and fourth position methyl. So ethyl comes first, so 3 ethyl, 2 hydroxy in the IUPAC order E, then H, then M, then 4 methyl, and it contains 6 carbon atoms. So hex 3, third position 1, 2, 3 in 5 ine oic acid, and E of ine will be removed because oic is what O is a vowel, and so acid there is a gap here. So 5 ine oic acid. The name of this, let's see, let's try to name this compound. So these compounds are is also ether, and two OSCH3 OCH3 groups are here. This is cyclopentane. So this one can name this compound as what? 1,2 dimethoxy. This is methoxy. This is methoxy. Two methoxy substituents. 1,2 dimethoxy cyclopentane. This compound, one, this is methoxy group and this is methoxy group. So one can call this as a dimethoxy methane. And dimethoxymethane means there is no position isomers in this case because methane means only dimethoxymethane. Methane is only one carbon atom is here, and so one carbon atom there is no different position. So 1, 2 will not be shown. This is dimethoxy. This methoxy and this methoxy methane. With the IUPAC name. For this compound, what we'll do, this is methoxy, and then the numbering we will done for the subsequent. And numbering always starts from here. The group contains O and then the subsequent methoxy substance 1, 2, 3. So this will become methoxy, and then at the second position methyl group is attached. So methoxy, 2 methyl, and 1, 2, 3 propane. So this is methoxymethane for the ethers name we write, and even if this methane, this alkane group contains a substituent, we have to write the name of the substituent as well. So this is the 2 methyl propane. So this compound's name is this. Now let's see these questions. So provide the IUPAC names for the reactants and products of the halogenation reaction. So questions may be asked in this way as well. So this is the reaction that is given. This is a halogenation reaction is already written. It means the halogen will be added to the double bond. Ation means addition and halogen is given. So this is ClCl. This is the chlorination. So this double bond is here CH3, CH double bond CH, CH2, CH3. And as you see here in this case, this is a cis group and they are attached the substituents at the cis positions because this hydrogen are here. So the same groups are at the same sites. This is the cis isomers. We will see the isomerism bit later on if you understand. So that's okay. And even if you don't understand, we'll see it later. So the compounds name numbering will start from here 1, 2, 3, 4, 5. So you can write the name of this compound as 2-pentene, 5 carbon atoms, 1 pentene, 2-pentene or pent 2 in. So one can also write pent 1, 2, 2 in, or if this is the isomers, in the case of isomers, geometrical isomers, we also write cis and trans to represent whether this is a cis compound or trans compound. Since this is a cis compound, so one may also write it as cis 2-pentene. How the cis comes, I'll explain it in the next class. Perhaps we will see this kind of isomerism. This is called geometrical isomerism. This compound has geometrical isomer. So this CH group, other this CH3 group can be here in this case, and hydrogen will be in this position. So that will be the trans isomer, and so that will be called a trans 2-pentene. So those they are different isomers, different compounds. So we can have this cis 2-pentene, and we can similarly have trans 2-pentene as well. So anyway, this is the most preferred name. Even if the till now whatever we have seen, you can write this name as well or this name as well. So the double bond, the Cl will be added to this double bond. So there will be one chlorine at this carbon atom, and this another chlorine be attached to this carbon atom, and so we can see then this compound CH3, CH, Cl here, Cl here, CH, CH2, CH3, and now we see the dichloro substitution, and this numbering will be again the same way 1, 2, 3, 4, 5. So 2, 3 dichloropentane is the name of this compound. Now let's see this question. That will be the last question. Then we'll start the next topic. So this compound is orthoethyl anisole. And orthoethyl anisole is given. It means what? It is 1,2 substitution is there because that is why the ortho term is used. And this base compound is anisole, and so the numbering will always start from the OMA group. And anisole is what? Benzene ring having OMA group, and so the numbering will start from OMA, and so it is actually this other name of this compound is 2-ethyl anisole. So either this compound is orthoethyl anisole or 2-ethyl anisole, same compound. So we will first write anisole benzene ring and OMA group. Then we will see ortho substitution at this. And ortho substitution means what? At the adjacent carbon, the carbon adjacent to the carbon which contains OM group, one ethyl substituent is added. So this carbon, or you may add this C2H5 group, you may add this carbon atom, the same compound. Now the para-nitroaniline. So aniline will first write. Tetranitroaniline also means 4-nitroaniline. So the aniline will write first, and then we see para. Para means what? 1,4 substitution. And the first number is already given to the carbon atom which contains NH2 group. That numbering we have already seen. So the nitro group will be attached at the fourth carbon, and so 1, 2, 3, 4. So nitro group will be here. Now this compound 2,3-dibromo 1-phenyl pentane. So the pentane is written. So we'll write first pentane 5 carbon atoms, and then we'll see 2,3-dibromo, and the second and third position will add dibromo means 2 bromine and 1 phenyl pentane, and then phenyl group will add the first carbon atom, and then we'll add the hydrogen atoms accordingly. And in the structure for the skeletal formula or the bond line structure, we can write this given. So phenyl group, phenyl substitution is what? The benzene ring. If it is attached as a substituent, we call it as a phenyl group. So this is a phenyl group. So one, just the phenyl group is at the first carbon atom. So one phenyl, and this is 2 and 3 dibromo. So this is the structure of this compound. The fourth compound is what? 4-ethyl 1-fluoro 2-nitrobenzene. So nitrobenzene is first. So anyway, we would write a compound, the benzene ring, and then you add nitro compound, and that nitro compound give number 2 to the carbon which contains nitro group, and then the fluoro will be just its adjacent carbon somewhere. So that is 1-fluoro and the 4-ethyl, and then 1 to the direction of numbering you have already seen 1, 2, then 3, fourth carbon atom you add ethyl group, and so this is the structure. So what is the structure? Benzene ring 1 nitro group. So this is the second, at the second position 2 nitro group, and the fluoro is attached. The fluorine will be somewhere, and that is given number 1, means it will be either in this side or this side. So fluorine I have added on this side. So 1, 2, then the numbering will go in this direction 1, 2, 3, 4. The fourth carbon atom contains ethyl group, and so 4 ethyl, and this is the structure of this compound. I hope you understand these things, and enough examples are given for the IUPAC nomenclature. From the structure you can derive the IUPAC name, or from the name itself you can derive the structure. There's enough examples we have already seen. We'll now start isomerism. I'll just give the brief introduction, few names. In details we'll go in next class. So what is the isomerism? If you see a compound, there are many different compounds. There are different compounds having same molecular formula. So different compounds means this compound will having different properties. So these compounds are different, having different properties, but when you write the molecular formula of this compound, we come to the same molecular formula. So such compounds are called isomers, and this phenomena is called isomerism. So the existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. So if you are saying different compound, two or more compounds, it means they have different properties itself. If they do not have different properties, usually, so and the same molecular formula with the same property, usually they will be the same compound. So different compounds, they will have different properties. They may not have all the properties different, but at least some properties are different in between those compounds. So even one of the properties different means they are different compound, and that will happen only if these compounds are different. I mean to say that. One example you can see here, and this the Wohler experiment we have already seen earlier when I introduced organic compounds, I think in the first lecture itself. And what we have, the Berzelius definition, he actually for the first time he proved that it was wrong, that the vital force is not required for the synthesis of organic compounds. And you see this example. So Berzelius, what he said, the vital force was responsible for the formation of organic compounds, because he tried to synthesize organic compounds and Berzelius failed to do in doing so. So he gave this definition. I think the vital force is required. But in 1828, Wohler, what he did, he synthesized urea from ammonium cyanate. Ammonium cyanate is an inorganic compound, and on heating this, he obtained urea. Urea is an organic compound, and so he said that vital force is not necessary for the synthesis of organic compounds. And so these examples, as you Let's go back to where we were. So here, so this compound, if you look the molecular formula of this compound, this is C, one carbon, two nitrogen, CN2H4O, or so CH4N2O, one can write CH4N2O, molecular formula of ammonium cyanide. Now this compound C2H here and two hydrogens here, CH4 again, N here, one nitrogen, N2O. So the molecular formula of this compound is also CH4N2O. Molecular formula of this compound is also CH4N2O. So they are isomers, but they are different compounds. This is an inorganic compound and this is an ionic compound. So this is an organic compound. This is an organic compound. This is an inorganic compound. And so they are isomers. They are different compounds having same molecular formula. This is a classic example of isomerism. So let's see the types of isomerism. So usually there are two types of isomers. One we call the structural isomerism. You see the difference in structure. And with the difference in structure, just by identifying different structures, we can easily understand these are isomers. However, what we call there is another type of isomerism that we call stereoisomerism. You won't see any difference in the structure as you see in this case. I said this hydrogen, if this hydrogen is on this side and this hydrogen this side, you just change the position of location of this hydrogen with this methyl ring. So hydrogen one, this hydrogen will be at this position and CH3 group comes here. The structure of this compound usually are same, the double bonds, the hydrogen atoms and different things, how they are usually. But what we see the difference in the positioning orientation of the CH3 and H groups. The relative positioning, with the change in relative positioning, we also see the different compounds and their properties are different, and the such isomerisms are called stereoisomerism. So stereoisomerism are of two types: geometrical isomerism and optical isomerism. The examples that we have seen here is the example of geometrical isomerism. Optical isomerism will see where the only the difference is in the properties, behavior of the compounds with respect to the plane polarized light. This definition and examples we will see later on. And this the structural isomers. Usually we consider four types of structural isomers. There is a fifth type of a structural isomer as well. So this is the structural isomers are chain isomerism. So the number of carbon chain that you see they are different. Like the neopentane, we have seen the one carbon contains four methyl groups. The neopentane or the N-pentane we consider. These are structural isomers, the same molecular formula, but the structure chain is different. And so this is called chain isomerism, and that is the difference in structure you see. Then the position isomerism, and the position isomerism in the equation nomenclature I have already explained to you. So where many places you see you change the position of one group, and you can still see like the, that is why where we saw the two on two with OL or something like the in the position of alkene, alkyne, and different substituents we are showing only in the case when the position isomerism is possible. It means, for example, you see this OMe group I can put even here, not here. So they will be position isomers. The name will be different. The compound and the difference is only at the relative positioning of different substituents, and that is called the position isomer. So the relative positioning, so position isomerism. Then the functional group isomerism. The functional group isomerism, particularly if you look at the aldehydes and ketones. The aldehydes and ketones is their molecular formula are same, but we know that in the aldehydes the carbon atom, the carbonyl carbon atom is attached to either two hydrogen atoms or at least one hydrogen atom must be there attached to the one carbonyl group in aldehyde. And on another side, it may be attached to hydrogen or the alkyl group. But in ketone, what we see, it is this carbonyl group is attached to different alkyl groups. So the ketones and aldehydes have the same number of carbon, and like the ethyl, if you look at the acetone, CH3, CO, CH3. There could be another compound CH3, CH2, CHO. The, both the compounds have same molecular formula, but one is ketone, one is aldehyde, and what we see the different functional groups are there. That is we call as a functional group isomerism. Then there will be another position that we call metamerism that I'll explain perhaps with the structure. So, and this functional group isomerism one can also alcohol and ether are functional group isomerism. Similarly, as we have seen the example in the case of Aldehyde and ketones, similar examples you see for the similar structural differences between ether and alcohol as well. The O oxygen atom in alcohol is at the terminus, it is between hydrogen and alkyl group, but in ether it is between two alkyl groups. There is no other difference, and so they are also functional group isomerism. And there is another type of isomerism that is called tautomerism. And these tautomers are chemical compounds that are readily interconvertible and differ only in the relative positioning of hydrogen atoms. And so these compounds actually they exist, tautomers exist in equilibrium, and so the hydrogen positioning of hydrogen atoms will be different into different compounds. Their structural formula other than that is the same, and so that is also we call as the structural isomerism. So tautomerism is also considered as the structural isomerism. What are these isomers means? What is the difference with the structure? Other things we'll see in the next class. I have just explained briefly what are different names and so on.